All right, we're continuing to discuss the changes that happen in our single sample t-tests compared to our z-test procedures. Put a little cheat sheet on the board there behind me because one of the steps that changes the most is that step 2, where we define the characteristics of the comparison distribution. We're still identifying the mean, the standard error, and the shape, but two of those three things change. We are already going to know the mean or be able to estimate it very easily, and we'll talk about how to do that. Remember, the standard error is going to be obtained instead of knowing the standard deviation of the population. We're going to estimate that population standard error by just using sample data. We calculate the sample variance, we turn it into a standard deviation and a standard error. So you're going to have to do some calculations in this step beyond just the standard error formula. The third piece is going to be a focus today, which is the shape of that comparison distribution. With our z-test, it was just a normal curve. That's all you had to say about it. Here we see there's a little bit more to it. Our shape now changes to what's called a t-distribution, and we also have to identify how many degrees of freedom it has. So our comparison distribution is a t-distribution. Some things about t-distributions, they still are symmetrical, unimodal. They look pretty similar to a normal distribution, but they don't have exactly the same proportions. Specifically, the fewer people you measure, the smaller your sample size gets, the flatter that curve gets. So let's see what this looks like. Basically, there's not just one t-distribution like one normal curve. There's a different t-distribution for each possible degrees of freedom. So here's what some curves look like. Up top, the dotted line here is our normal distribution. Then we see two t-distributions, one for a medium size but still small sample of how many people in this sample? You can just add 1 to it. 21 people in that sample, 20 degrees of freedom. 6 people in this sample, 5 degrees of freedom. Here's what you note. The fewer people that you measure, the flatter that curve gets, which means that scores near the mean become a little bit less frequent and less probable. And conversely, the farther away you get from the mean, as you get into the tails start to get fatter with those reduced sample sizes. That just basically means that scores that are far away from the mean become substantially more probable, more commonplace as those degrees of freedom drop. So we have to account for this in our step 3 when we are going to get those critical values. But first, again, the t-distribution is a point of emphasis for not just this module, but for the next module as well. Again, one of the main takeaways, it's not a normal distribution, but it is similarly shaped, but there are as many t-distributions as there are different types of degrees of freedom. The reason why, remember that whole discussion of the sampling distribution when we talked about variability and sample means, the fewer people you measure, the higher likelihood of sample means that are really far away from the population. They become more probable as your sample size gets lower. As your sample size gets higher, it tightens up, and the distribution compresses steadily. Notice the normal distribution assumes you're taking infinite scores. So that's why, again, it doesn't matter how many people are in your sample when you're dealing with a normal curve situation, because it's assuming that you are drawing, again, a great many scores from that population. In our t-distributions, as your degrees of freedom drop, the center of the distribution also drops and the tails rise. They get thicker, they get more common. What that means for our purposes is the critical values are going to change with the degrees of freedom. Specifically, the fewer degrees of freedom you have, the farther away from the mean your critical values are going to get. Because again, you have to get farther and farther away to be in that most extreme 5% or 1% that's described by alpha. So lower degrees of freedom, your critical values are farther from the center. Higher degrees of freedom, your critical values get closer to the center. With enough degrees of freedom, if you measure enough people, your t-distribution eventually becomes identical to a normal distribution. So the effectiveness here is mostly for smaller sample sizes because with a big enough sample size, the two distributions become one and the same, the normal and the t. So how do we find those critical scores on a t-distribution? We can use what's called a t-table. Remember, we used the normal curve table for some exercises, looking up critical values and that sort of thing. A t-table has also been uploaded to this module. Just like the normal curve table, I'm not going to have you use this on an exam. It's just for kind of getting a mechanical sense of where these critical values are coming from. They're not just magic numbers that come from space. They correspond to specific aspects of the design. So here, notice this doesn't look exactly like the one that you're going to be able to download, but we have rows for each degrees of freedom, and then we have, again, different p-values, or excuse me, different alpha values. for both one and two-tailed tests. And the short version is, the farther down the list you go, you can see that the critical values get closer and closer to the mean as you're measuring more and more people. At the very bottom, where infinite scores are assumed, these are actually identical to critical values for the normal curve. So if you have a degrees of freedom that actually isn't represented on the table, you'll notice it starts skipping numbers at some point. We use the next smaller degrees of freedom value. The reason why is if you use the smaller degrees of freedom value, the critical values get a little farther away from the mean. That sets a higher bar for rejecting the null. And remember, that's when in doubt, we always make it harder to reject the null. So again, long story short, you don't round to the closest number, you don't round up, you use the closest lower number to your actual degrees of freedom. Or in the real world, you just use software, but we kind of do it the old school way here to learn the concepts. All right, last missing piece. In step 4, we're going to have to calculate a test statistic. We calculated a z-score there in module 7. Now we're going to calculate a t-score. Here's your t-score formula. If you remember the z-score formula, you'll notice this looks almost identical. There's only 2 changes. One of them, obviously, the z has been changed to a t. What's the other one? The numerator is exactly the same as the z-score formula for sample means. It's just the deviation between your sample mean and the population mean. Numerator's changed. This was sigma sub m, sigma with a subscript of m, which is the population standard error. Here we have the sample standard error because we don't know the population standard error. The sample standard error that we're using to estimate that population standard error. So that standard error you calculate in step 2 is going to carry forward and be the denominator here for your test step. But conceptually, it's just a deviation score divided by standard error. So it tells you how many standard errors apart your sample mean and population mean are. Pretty straightforward. If you know the mean of the population, you're just plugging in numbers that you already got. 2 of them are from step 2, 1 of them you already have. If not, you can oftentimes figure it out pretty quickly from the null. So for example, those chance standards. If I was testing whether a coin was fair, I know what the population mean should be for the number of heads I would get out of 20 coin flips. I should get 10 on average. Again, that doesn't have to be already present for me to figure it out very quickly. Here's a little hint. I might make you do this at some point. Maybe on a quiz, maybe on an exam. You might have to estimate a population mean based on basic probability or expectation. So be prepared to do that. Your book's going to make you do that once or twice as well. That's the end for this section. We have done all the setup for our hypothesis testing in this single sample t-test framework. Next up, we are going to review those 5 steps and walk through an example together.